Hi, everyone. Welcome back to Dave's Math School. I'm your host, David Terr, and I'm doing a several part series about infinity. This is part two, and this one's entitled Rational Numbers Are Countable. I guess I have to explain what that means first. So, what do we mean by a countable set? Well, a countable set is just a set where you can sort of count all the elements. It can either be finite or infinite. Finite sets are example of countable sets. I mean, if we just had sets with, say, four elements each, we could say the x could be 1, 2, 3, 4, y could be 2, 4, 6, 8. So those have the same size because you can pair them all off. You just pair off every number in x with twice its value in y. And it doesn't have to be finite in order to do that. It could be countably infinite. So if you think about just all the counting numbers or all the positive integers, if you like, x could be the set of all positive integers, capital X, and y could be the set of all positive even integers, and they still pair off in the same way. I mean, you can still pair one with two, two with four, three with six, x with 2x in general, where x is any positive integer. And even though both of these sets are infinite, they both still have the same cardinality. And that cardinality actually has a name. It's called Aleph null. And this slide just kind of explains finite sets and countably infinite sets. So a finite set is just what it says, is a set with a finite number of elements. But a countably infinite set is a set with an infinite number of elements, but it's countably infinite. As it turns out, there's different sizes of infinities. I'm not going to get to that in this lecture, but this thing we call Aleph null, this Greek letter, this is a Hebrew letter, Aleph, by the way. It's the first letter of the Hebrew alphabet. And they put a little zero subscript to the lower right. So that's what we call Aleph null. And this symbol means the smallest infinite cardinal numbers. This is the size of the integers, if you like, or the size of the counting numbers. And the last video I did, I showed that you can actually pair. I mean, I just showed that you can pair all the integers with all the even integers. And actually, you could add all the odd integers to y. Notice that even though x and y have the same size, they both have cardinality Aleph null. You can still add all the odd numbers to y, and then you get back x. So it's kind of weird because x is actually isomorphic. It has the same size as a proper subset of itself. And that is a property of infinite sets. As a matter of fact, you can define an infinite set as a set with that property, such that it's isomorphic to a proper subset of itself. That's not true for any finite sets, but it is true for infinite sets, and that's kind of the basis for Hilbert's hotel, which I talked about last time. But I'm going to show you something else, which I think is in a way maybe even more remarkable than Hilbert's hotel. You might wonder how many fractions there are, how many rational numbers there are. I think you guys learned about rational numbers back in grade school, and you know that a rational number is just a fraction, basically. It's a number where it has both integers in its numerator and its denominator. Of course, the denominator can't be zero. If you want the fractions to be reduced, then the numerator and denominator should have a common divisor. But that just kind of restricts the number of pairs. So here's something I think is really remarkable. It turns out there's still a one-to-one correspondence between the positive integers, the counting numbers as you like, and the rational numbers. You might not think that's possible because I mean this is just positive rationals, but the same is true for negative rationals. So here we're just concentrating on positive rationals. It really doesn't make much difference. But here's the trick. So like I said, every positive rational number can be represented as a fraction of say a over b, where a and b are both positive integers, and you don't really have to worry about them being relatively prime. That's just a restriction. If you did that, you would get fewer. You just eliminate some of the numbers on this list. But here's how you do this. So you kind of do the look at the zigzag path. See the arrows? So you start with 1, which is just 1 over 1. And then the next number you get in your sequence is 2, which is 2 over 1. And then if you want a half, you just move up and to the right. That gives you 1 over 2. So you can see that the numbers, the row numbers correspond to the numerators of your fractions, and the columns correspond to the denominators. So but the zigzag path gives you a one-to-one correspondence between all the counting numbers. You just count how many arrows you've done. So I guess 0 arrows would be 1, or maybe 1 if you want to start with 1. And then 1 arrow takes you to 2. 2 arrows takes you 1/2. 3 arrows takes you to what is it, 2/3? Or no, 1/3. And then you just keep going. The fourth one takes you to 2/2. That's the same as 1. You can skip that one if you like. And then I guess the fourth arrow would take you to 3 over 1. So you can just keep going like this. You can count the number of arrows it takes to get to any fraction you want. And it's always going to be a finite number of arrows. So what this diagram kind of proves, there's this one-to-one correspondence between the counting numbers, the positive integers, and the set of positive fractions, positive rational numbers. So even though the rational numbers are dense in the real numbers, I mean, what that means is that no matter how small an interval you pick in the real numbers, you can always find a fraction in that interval. You'd think there'd be a lot more fractions than integers. Because, I mean, for one thing, the fractions include the integers. The integers are a proper subset of the fractions, but not only are they a proper subset, it looks like there's a lot more fractions than integers. Because, like I said, they're dense in the real numbers, and so you might think there's almost as many fractions as there are real numbers, but actually that turns out to be false too. The next video I'm going to show, I'm going to actually prove that there's more reals. So even though the fractions, the rational numbers, there's the same number of rational numbers as there are integers, it turns out that the size of the real numbers is actually bigger than the size of the rational numbers. It's a thing we call C, the continuum. I'll show that in my next video. But anyway, I thought you'd be interested to know this. So it's kind of a step beyond the two examples I gave yesterday when I was talking about Hilbert's Hotel. But anyway, that's my video, and I hope you enjoyed it. Thank you for watching, and long live math. And I'll see you next time.